Last episode we said a matrix transforms a vector, but we never said how. The answer is a single operation repeated billions of times that powers every neural network ever built. It's so important that chips are designed around it. Today, the dot product and the matrix multiplication built on top of it. Start with the dot product. Take two vectors of the same length. Multiply them together one slot at a time. First with first, second with second. Then add all those products into a single number. Two lists of numbers go in. One number comes out. That's the whole operation. Simple. But what that number means is the interesting part. Let's do one. Take 1, 2, 3 and 4, 5, 6. 1 times 4 is 4. 2 times 5 is 10. 3 times 6 is 18. Add them. 4 plus 10 plus 18, 32. One number summarizing how those two vectors relate. Now, why does that number matter so much? The dot product measures alignment. When two vectors point the same way, their dot product is large and positive. When they point in opposite directions, it's negative. And when they're perpendicular, completely unrelated, it's exactly 0. So the dot product is a similarity score. How much do these two vectors agree? That single idea shows up everywhere. Strip out the length and keep only the direction, and the dot product becomes cosine similarity, literally the cosine of the angle between two vectors. 1 means identical direction, 0 means unrelated, minus 1 means opposite. This is how search engines and recommendation systems compare things, turn everything into vectors, then rank by how aligned they are. Similarity becomes a single number. Now a payoff. Remember the neuron from episode 1? Multiply each input by its weight and add them up. That is exactly a dot product, the input vector dotted with the weight vector. Every neuron is asking one question: how aligned is this input with what I've learned to look for? The entire network is dot products all the way down. So what's a matrix times a vector? Just many dot products at once. Take each row of the matrix, dot it with the vector, and that gives you one number of the output. A matrix with 100 rows produces 100 dot products. 100 neurons, each checking the same input against its own weights. One matrix vector multiply is one whole layer firing. Step up once more, matrix times matrix. Every cell of the result is the dot product of a row from the first matrix with a column from the second. Row 2, column 3 dotted together lands in position 2, 3. Do that for every row column pair and you fill the whole output grid. It's just a lot of dot products organized neatly. This is where shapes bite. To multiply an m by n matrix with an n by p matrix, the inner numbers, the two ends, must match. They're the length of the vectors being dotted, so they have to agree. The result takes the outer dimensions, m by p. Get this wrong and your code throws the most common error in all of deep learning. Get it right and everything lines up. Once you see it everywhere. A feed-forward layer, matrix multiply. Attention, the engine of transformers. A stack of matrix multiplies, comparing embeddings, projecting, mixing, matrix multiplication. Training a giant model is, at the lowest level, just trillions of dot products being computed over and over. The whole field runs on this one operation. And because it's the same operation repeated, it's perfectly parallel. Every output cell is independent. They can all be computed at the same time. That's why GPUs have thousands of cores and why Google built the TPU, a chip whose entire purpose is matrix multiplication. The hardware of the AI boom exists to do this one thing faster. So here's the whole hierarchy in one breath. A dot product turns two vectors into a similarity score. A matrix vector multiply is a batch of dot products, one layer. A matrix multiply is a grid of them. Stack these, sprinkle in the nonlinear bends from activations, and you have a neural network. It really is dot products scaled up. That's the operation at the center of everything. The dot product measuring alignment assembled into matrix multiplication. Master this, and the inside of a neural network stops being mysterious. It's just vectors being compared and combined. Next time, we bring back calculus and generalize the slope to many dimensions, the gradient and the Jacobian. See you there.